Hello, and welcome to another session on sequential circuits. This session will look at the T flip-flop, or the toggle flip-flop. And toggle is what it sounds like. The T flip-flop has two basic functions. It can hold the present value of the output, or it can toggle it, change it to its opposite state. The T flip-flop shown here is leading edge triggered. When the clock goes from low to high, the output Q will look at the input T and decide what to do. On this first leading edge, it sees a 0, so it will hold the value of 0. On this next leading edge, it sees a value of 1, so it will go to its opposite state. In this case, it'll go from 0 to 1. Subsequent trailing edges, or leading edges, all will see a value of 0 at the T input, so we hold the value of Q all the way through this leading edge here, where T is once again 1, and we change to the opposite state of Q from 1 to 0. On this last leading edge, T is still equal to 1, so we'll once again toggle the output, this time going from 0 to 1. Now the T flip-flop, like our other flip-flops, can be described with a symbol. And the symbol is very similar to the D flip-flop. There's one input, this time T rather than D. There are two outputs, Q and its inverse, Q naught. And there's a control signal input, clock. And the triangle here at the symbol of the clock input indicates that this input is trailing edge triggered. So this particular flip-flop will only change its output when the clock is going from high to low. And we've already discussed there are two functions of the T flip-flop, hold and toggle. And we can expand that functionality into the complete truth table, reflecting all possible input combinations of T and present states Q. When the input T is 0, the output Q holds its present value, as does Q naught. And when the input T is 1, the output toggles, either from 0 to 1 or from 1 to 0. Let's take a look at a possible implementation of the T flip-flop. This particular implementation uses a D flip-flop in combination with an XOR gate to implement the T function. And to analyze how it works, let's take a look at the two possibilities, T equal to 0 or T equal to 1. If T is equal to 0, then we can take a look at the two present states of Q. If Q is equal to 0, then the next state is equal to 0. Because 0 XOR 0 is simply 0, and on the next trailing edge of the clock, that 0 will get transferred through the D flip-flop. If, on the other hand, Q is equal to 1, 1 XOR 0 is 1. So if toggle is in the 0 state and the present state of Q is 1, the output Q will be 1. And that's how we get the hold function for the toggle flip-flop. Now in the other condition, when toggle is equal to 1, if Q now is equal to 0, 1 XOR 0 is equal to 1, and that transfers through on the next trailing edge. So the next state, when Q is equal to 0 and T is equal to 0, is Q equal to 1. And when present state of Q is equal to 1, 1 XOR 1 gives us an output of 0. 0 transfers through on the next clock cycle and gives us a new Q, or a next state Q, of 0. And that's how the T flip-flop is implemented to produce both the hold and the toggle functions. Now we can take a look at this on the timing diagram shown here and just look at how the trailing edge T flip-flop works in real-time operation. So on this first trailing edge of the clock here, what happens to Q? Well, that's a good question. Where does it start? And that means that somehow we have to reset or establish the initial value of Q in this T flip-flop, or it won't work properly. It'll continue to produce an undefined state, because if Q starts in an unknown state, it will remain unknown whether it holds or toggles. So we're just going to assume here that it's reset to 0 in its first stage. Then at the first trailing edge of the clock, when toggle is equal to 1, it will just change state. On the following trailing edge, toggle is equal to 0, so it will hold its value. On the following trailing edge of the clock, t is equal to 1, so it'll toggle to its opposite state. And on the next trailing edge, it's still equal to 1, so it'll toggle again. And then the last trailing edge, toggle is equal to 0, so it will hold its state. And that's how the T flip-flop works. This T flip-flop can only perform 2 functions, but nevertheless it's valuable in digital logic and systems design. And it can be implemented as shown here using an XOR gate and an existing D flip-flop, or other combinations of basic logic gates using similar design techniques. That's all today for the T flip-flop. Thanks for joining us as we continue to explore the world of digital logic and systems, and we hope you'll join us again soon.